Join the conversation.
Join the conversation.
You're with Cape Talk.
You are indeed at 9:33. Time for us to welcome back the Naked Scientist, Dr. Chris Smith, consultant virologist at Addenbrooke's Hospital in Cambridge. Every Friday, just after 9:30, joins us to answer your questions. Keep them coming through via WhatsApp 072 567 1567. But of course, if you want to call in, you'll jump the queue and you can call on 021 446 0567. Good morning, Dr. Chris Smith. Good to have you
morning,
back.
Clarence. Morning. Do you know, I had a really interesting week this week. I bumped into a couple of scientists at the hospital I work at. They actually work at the MRC Laboratory of Molecular Biology. And their opening gambit was, we think we might have discovered how life got started on Earth. Then they toned it down a little bit. But this is an extraordinary piece of work. It's in the journal Science this week. And Phil Holliger and his team have worked out how to make tiny molecules. This is the molecule RNA, which is a chemical relative of DNA. They have found a small molecule, it's just 30 genetic letters long, that can copy itself. And so their thinking is that what could have happened on the very early Earth 4+ billion years ago is that there were enough chemicals washing around in warm little pools that some of them spontaneously could have assembled into short strings of what we call RNA building blocks in this way, producing something capable of folding itself into the right shape and size to then become autonomously replicating. So it can just basically make copies of itself. Now, they don't think what they've got is the first form of self-replicating machinery on Earth, but this shows us how it can happen, and the fact that this is much, much smaller than anything anyone's discovered before makes it that bit more likely that this idea is right, that this is how, from spontaneous chemistry, biology could have arisen. Isn't that extraordinary?
So that is from a chemical into a living life form. Is that what you're saying?
Well, we don't think life just suddenly popped into existence all at once. It must have been an incremental series of stages. And arguably, one of the most important stages is having some kind of information that's capable of making more of itself. Our genetic information, our DNA, in almost every single one of our cells, there's a couple of meters of DNA all strung together, 3 billion genetic letters long, and it makes a copy of itself when one cell splits into two cells. Now, early life would have been doing something similar. It must have had a way of passing on that information, those instructions. And so, arguably, before we had to worry about how cells came along and wrapped themselves up in membranes, etc., there had to be a mechanism by which the genetic information began to copy itself. And that's always been the stumbling block, because it's a bit of chicken and egg. How on earth can you get something that complicated to evolve in that way? And people had always pointed the finger at this molecule RNA. It's in all of our cells. DNA turns itself into it and uses it. But how could you end up with something capable of making more copies of itself in this way? And although scientists had found huge versions of this, where big RNA molecules that could do it, they were so big. People said, well, how on earth could that have naturally just strung itself together in the right way at the right time by the time life got started for that possibly to be feasible? But with a much smaller molecule capable of doing this, it shows that, in fact, it can be done. And this is much more likely, therefore, that that's how some of these early life forms could have got started.
That's exciting. And then they toned it down.
And they what?
You said then they toned it down.
Well, no, I mean, they were joking when they were saying that we found the secret to life, because that's what Watson and Crick said. I mean, they rushed into the Eagle pub in Cambridge in 1953 and said, we have found the secret of life. Now, I mean, arguably, one of the secrets of life is DNA and the genetic code, and that's what Watson and Crick had discovered. What these guys have discovered is a finger pointing towards a direction that makes this hypothesis, called the RNA world hypothesis, about the origin of life, that little bit more likely.
Okay, let's go to Maeve's question. Fascinating what we are learning. Maeve wants to know, why is glass clear when the sand it's made from is opaque? What happens to the atoms during melting that suddenly lets light through?
Hello, Maeve. It's exactly the same as if I pour a glass of water from the tap and you hold it up to the light. You can see through it. It might bend the light a bit and you might see a slightly deformed Clarence behind the glass, but you'll see Clarence through the glass of water. Take that water and freeze it, and turn it into lots of ice crystals, hey presto, you have something white. Very similar to what sand does. So what's happening is when you have lots of tiny crystals, you've got lots of surfaces. And when light goes from one medium, the air, into another medium, in this case we're talking water, but it could be glass, it changes speed because the speed of light is not constant. There's a maximum to it, but it's not constant. And when it changes speed, it bends. And if it changes speed enough, it bends enough to come back towards you. In other words, you end up with a mirror surface. So when you have lots of tiny ice crystals, which are analogous to sand, the light is reflecting off of those ice crystals back at you because it's been bent by so many of these surfaces and crystal surfaces that you see all the light reflected back and it looks white. But when you link all of the water molecules together to make one solid ice cube, which is what glass is, turning sand into glass, or you have just the liquid, the light goes straight through, because although it will bend a bit when it goes from the air into the water or the air into the glass, it's only going to do that once on the way in and once on the way out, which means you don't scatter all the light all over the place and reflect a large amount of it back towards your eyes. So it looks transparent rather than the opaque sand or snow.
Zuki's on the line. Welcome, Zuki. Go ahead for Dr. Chris Smith.
Hi, Clarence, and hi, Dr. Smith. Effervescent tablets are supposed to be dissolved in water before taking them, but I like taking them without doing that. I take them dry. So my question is, are there any dangers to doing that? What's the worst that could happen?
Most likely danger, Zuki, and hello, good morning, is the socially unacceptable effect. And you'll know what I mean, because the effervescence is carbon dioxide gas. And if that's produced in your glass, it makes your glass fizzy. If it's produced in your stomach, it makes your stomach fizzy, and you will then have to find a route out to the outside world for that gas, which is going to take up a lot of space. Now, normally from the stomach, that's going to come upwards. So perhaps if you're in the Middle East where it's socially acceptable to let rip, then that's fine. But in many cultures and countries, it's less acceptable. So it's better to have that fizzing going on in the glass. What's actually happening with those tablets is you have two acid anhydrides. An acid anhydride and a base. The acid is often citric acid. It's a dry powder and it only releases its acidic property when it becomes wet. And the base, in other words, the alkaline substance, is often sodium bicarbonate, what's in cooking powder, baking soda. When you make them wet, you liberate hydrogen ions, the acid part from the citric acid, and this can see the alkaline part of the sodium bicarbonate. The acid attacks the sodium bicarbonate. It produces the CO2, carbon dioxide, as a gas, and water. So you get some dissolved sodium citrate, and you get some water, and off goes the carbon dioxide. It's not going to harm you if you swallow these tablets, probably, but it's probably socially better to let the gas come out in the glass and then have the fizziness in the water and enjoy that rather than it all coming out in your stomach.
Then we got a question in from Roger. It is about foot and mouth disease. It has been declared a national disaster just last night by our president. Roger says it's rampant in South Africa right now. Can one drink the milk from an infected cow or eat its meat in a burger?
The problem with foot and mouth disease is whilst this virus does not pose a threat to humans, it is devastating for farmers' livelihoods and livestock. And it's extremely long-lived in the environment, which means that once you have an infestation with it, it's really hard to shift, which is why countries go to extraordinary lengths to make sure that it doesn't spread. And this is why there are really strict import controls on moving animal products, meats and so on, around the world from countries where this is a problem to countries where they have successfully prevented it being a problem. In theory, this virus doesn't infect humans, therefore it's not going to be a problem for us. But anything that makes an animal ill could cause other problems and could therefore pose a threat to us, which is why we tried not to get any of this stuff into the food chain, not least because it then propagates the problem on. You've still got foot and mouth viruses around, which could then get elsewhere. So it's an economic disaster, it's a livestock disaster, but it doesn't pose a threat to us as humans because those viruses are not going to infect us.
I think just on that topic, John sent us a message and he drew attention to the suffering of the animals. Um, uh, and yeah, it was quite a serious note that he sent to us. Just how bad is the suffering? Does it kind of live up to the picture painted by John?
It's a serious impact, and in the same way that there are viruses we can catch, which will be devastating for us, but they don't seem to cause a problem for animals, the same is true. And in some cases, the viruses just can't affect us. If you take norovirus in humans, it's a calicivirus. When we catch that, we know all about it. We're sick and bad. You can be sick right next to your dog, and your dog will not catch it, but your friend, brother, sister, mother, father, they will. So it really comes down to horses for courses here. Some viruses
Yeah.
affect some hosts and not others. These animals, if they catch it, can become seriously unwell. But as I say, it's something we don't want into the environment, because once it's
Sure.
in an environment, it's very, very stable, this virus. It can sit in the soil or on the soil for ages, weeks. And this means that although you think you've got rid of it, along comes a healthy animal again, grazes, and it's in. And then you've got it starting all over again. And yes, those animals can become unwell.
Yeah, but he described it as seriously unwell, beyond seriously unwell. He said the kind of pain and the suffering that they endure, yeah, unimaginable. And I think it is that corroboration, Nelly, that we required from you. But let's go on to another question. And this time round, it is from SJ. Why does some people's accents change if they emigrate to another country?
Yeah, that we all know people who appear to catch accents much more readily. I've got a very good friend who lives in Australia. He moved there from Middlesbrough in the UK about 40 years ago, and he still sounds like he comes from Middlesbrough in the UK. No contamination of his accent by Australian accents. I mean that in the nicest possible way. On the other hand, I know people who, within minutes of being in another country, already begin to catch the accent. We think that part of this is age. When we're younger, we definitely catch accents more easily than when we become more staid in our ways as we get older, more rigid. And also some people catch accents throughout their lives more readily. And it often comes to people who are more empathic. And so I suspect that what's going on here, in the same way that as a social species, in the same way, birds of a feather flock together, humans are a social species. We stick together, we work together, we live together, we do all things together because we are extremely successful together. I think there's an African proverb, isn't there, that if you want to do something fast, do it alone. If you want to do something well, you do it together. And that's why humans are so successful. But part of what bonds us together is adhering to social norms, being like each other, singing from the same song sheet, literally as well as metaphorically in this case. So we learn to fit in with each other, and the people who are very, very good at doing that, people who are very good at getting into other people's mindset, often tend to merge their way of speaking with other people's ways of speaking. That's how accents probably distilled out of society in the first place, and some people are a bit more vulnerable to fitting in really well than others.
Question in from Apple. I'd like to hear Dr. Smith's view on the condition trigeminal neuralgia. It's a condition that causes episodes of intense and sudden facial pain on the one side of your face. In my case, on the left side, it feels like an electric shock. It's extremely painful and uncomfortable. It affects daily activities like tooth brushing, eating, washing, etc. I've suffered for the past week, and medication seems to be ineffective. Is there a cure? And how quickly can I expect relief?
Yeah, nasty. People who have this do talk about debilitating pain. The trigeminal nerve is the sensory nerve of the head and face, and it's also known as the fifth cranial nerve, and has three distributions: one around your eye, one on your cheek, and one on your chin. And those three branches are vulnerable to this. And what can happen is that you get so-called neuropathic or referred pain in the territory supplied by the nerve. So, in other words, although the face has nothing wrong with it, it feels incredibly painful in that area because that's the area supplied by the branch of the nerve that's got the problem. Now, one cause can be a blood vessel that presses on the nerve and causes that pain, and this can require surgery to fix it. There can also be infective causes for this, herpes viruses, which reactivate in our nerves in certain territories, can leave you with a neuralgic state, a post-herpetic neuralgic state in the aftermath. And again, sometimes, and back in history actually, people have resorted to the step of cutting the nerve in order to try to get relief from the pain. That actually made their herpes worse because it reactivated the virus. So it really depends on what the cause is, making sure you got the diagnosis right, investigating accordingly, and then the treatments will be dictated by what's causing it. If it's something anatomical or structural that can be fixed, then that may need imaging and a surgeon. Sometimes, if it's a chemical or so-called idiopathic cause, we don't know what's irritated the nerve, then it's a neuropathic pain state, and that may require medication, which is capable of damping down those signals, which are aberrant signals coming from the nerve. And there are various drugs that can be used for that, but they do have side effects, and sometimes the treatment ends up being worse than the disease. So you have to be a bit careful what you wish for. But certainly this is no substitute for getting help. So if this is just started and it's causing you serious debilitating symptoms, this should definitely be investigated. And then once the cause is known, then an appropriate treatment can be prescribed.
Sandy writes for The Naked Scientist, and keep your questions coming through for Dr. Chris Smith, consultant virologist at Addenbrooke's Hospital, Cambridge. At 10 minutes to 10 o'clock, you can send the message via WhatsApp on 072 567 1567. You can call and beat the queue on 021 446 0567. I've asked you about ivermectin being used for cancer before, and you said that no trials have been done, and apparently cancer patients have had success with the product. Could you tell me why no trials have been done with this product? My son has rectal cancer.
The bottom line with any kind of treatment or drug trial is that there has to be biological plausibility in order to pursue an avenue. What we mean by that is there has to be a mechanism of the disease where you can see that the drug in question or the molecule in question, because drugs are molecules, will make an active difference to that particular mechanism. So in other words, you understand the clockwork and you've got a spanner of the right size and you throw that spanner into the mechanism to clog up the clockwork, or you've got a pry bar that you can use to lever the mechanism around. If the drug does not fit with the mechanism, there's no point in throwing something which could have side effects, and all drugs have side effects. If you can't identify a mechanism by which an agent might make a difference, then this might just make the person worse, and that would arguably be a much worse situation to be in. So things get tried when there's a clear path to seeing how they can make a difference, or because we have seen that there's an association between the use of a drug and a lower representation of a particular outcome in people for other reasons who have that drug. So, for instance, we've begun now to realise, often thanks to electronic medical records, that people who are on a drug for one disease sometimes develop another condition at lower likely or lower levels or lower rates than the general population, than they would be expected to by chance. And then when we look more closely, we find that a side effect, if you can call it that, of one drug is to stop other diseases that it's got nothing to do with, and we find a so-called off-target effect. So people are always looking for this. So once we see that kind of association, we often learn a bit more about the disease process and also a bit more about the drug. So there may be a path that a drug which is developed to treat worms might find itself being used to treat cancer, but just because some people say they've taken something and they had a good outcome, it doesn't mean that the drug did that. And so one's always very cautious about these sorts of things, and the biggest overriding concern is to make sure we don't make a person worse or forego other evidence-based treatments in favour of something that's not evidence-based, and thereby miss out on an opportunity to treat someone with something we do know works and make their condition worse.
Let's go to the voice notes. Let's tick off some of them. Joe, let's take a listen.
Good morning. I wonder if you'd ask the naked scientists the difference between colloidal silver and quantum silver. Apparently, they're both natural antibiotics. Okay. Thanks very much.
I'm not sure the subtlety of the quantum bit, but I wonder if they're talking about quantum dots or the nano dots of silver versus colloidal silver, where you've actually got silver in solution. But the premise of the question is silver, does it have antimicrobial properties? And the answer is it absolutely does. If you've got small amounts of silver in solution, it's highly toxic to microorganisms. If you decorate surfaces with silver particles, they're highly toxic to microorganisms. And people are now actually making surfaces functionalized with silver particles, which I think is where the quantum silver word comes in. And these tiny particles provide a big surface area for chemistry. And silver, being quite reactive, will facilitate the production of species, chemicals, which are toxic to microbes, and in that way sterilize the surface. And there's evidence that you can do this in water, for example. If you put a little bit of silver in water, you can sterilize water that way. And I think there's some claims that if you've got some dirty water and you put some silver in the water, shake it up, put a bit of oxygen in, the silver in the water reacts or helps the oxygen to produce reactive forms in the presence of sunlight, and that can kill the microbes. So I think that, yes, silver does have antimicrobial properties. It's being explored actively and used to make self-sterilizing surfaces to protect door handles, the insides of fridges, work surfaces, hospital equipment, and certainly has a track record for that. What the best way of doing it is, though, I think people are still actively exploring this to see what else can be achieved.
Let's go to Brian's voice note, Joe.
Is Lyme disease contagious?
Hello, Brian. Lyme is Borrelia burgdorferi. It is a bacterial infection, and yes, it is a contagious infection, as in you catch it from something, but when you've got it, you don't give it to another person. We don't transmit Lyme between us. At least I've not heard of cases of that, because most people who get it treated and they eliminate it. The source into the human is a tick bite. And what happens is that the ticks, and a small proportion of ticks of the whole population, carry this bacterial infection. Those ticks, when people pick up a tick, bite the person, and because ticks are blood feeders, the tick's saliva has the bacterium in it, and when the tick feeds, the bacteria can get out of the tick into the bite wound, and from there it then spreads systemically through the person. The giveaway is that after a person gets the tick bite, you then develop a so-called target lesion. It looks like a bullseye painted on your skin with a red patch, a white patch, another red patch. It's also called erythema chronicum migrans, I think, isn't it? But that is the giveaway that you've got Lyme. Thankfully, it is very sensitive to antibiotics we routinely have. So a quick diagnosis, if you think you've been exposed, you've had history of a tick bite, you've got the evidence of the skin lesion, and then you get some of the other symptoms, and once it begins to spread through the body, there are other symptoms. You can get neuro-Lyme. It's not very nice. You need to get treated, and there are antibiotics that you need to have promptly to make sure that it is properly treated. But because we don't go around biting each other and spreading our body fluids onto each other, there shouldn't be a human-to-human transmission chain of Lyme disease. It comes to us and is transmitted to us from the ticks that carry it naturally.
A quick one, Dr. Smith. Space dust falling on us, hydrogen escaping our atmosphere. Are we gaining or losing mass on planet Earth?
The Earth is achieving or adding about 50,000 tonnes of mass in the form of incoming falling space dust every year.
Wow.
But we are losing a bit of hydrogen and helium all the time. I did the calculations about 20 years ago, actually, and I think we calculated that we are net losing mass to space every year because we're losing more hydrogen than we're gaining in space dust.
Okay, that's it. We're going to have to wrap it there. Big thank you to the Naked Scientist. Every Friday, just after 9:30, consultant virologist at Addenbrooke's Hospital, Dr. Chris Smith, answers your questions right here